Hey everybody! In this video we will look at two different ways in which you can solve the robot simulator exercise. The robot simulator exercise is one where you get a robot, and that robot has two things. It has a bearing, so the direction that it's looking at, and a position, which is an X and a Y position. Then there are three different movements that the robot can make. One is to turn right, one is to turn left, and the other is to advance. So if you have a robot that's on position 3,8, so X is 3, Y is 8, and if it would move north, it would be ending up at the same X position, but the Y minus 1, plus 1, because it's moving north. So the way that the exercise works is that you have to create a robot based on a direction and a set of coordinates, and then you get a string of letters, and those letters are the moves that the robot can make. So you have the letter R stands for turn right, A means advance, and L means turn left. So you get a starting robot, you get the position, then you apply the instructions, and in the end the robot should be at a specific location with a specific bearing. So that's what we're gonna implement today. First of all, let's see what our initial situation is. We have a module named Robot Simulator, and there are two types being defined. One is a direction, which is a discriminated union, which contains four different values. It's either north, east, south, or west. And the other is a position, which is an alias for an int tuple. So then we have two functions that we need to implement. One is create. The create function takes two parameters, the first being the direction and the second one being the position. And what it returns is actually left open. So we don't have an explicit return type. And this is for a very specific reason, because we want students to allow themselves to choose different implementations of a robot. So there are many different ways in which you could have this data be modeled. And we're going to take a look at some of the different ways that you can do that. But the exercise purposefully leaves this open to you, the student. And then there's the move function, which takes the instructions string, so that's the RAL combination of the letters, and the robot to apply the moves to. And in the end, what it should return is, again, the robot, so the new robot state. A couple of things to note, that we could implement this in a ton of different ways. But there is, in general, maybe 4 different ways in which we can do this. I'd say the first being a discriminated union, second being a record, the third being a tuple, and the fourth being a class. So a class would only really make sense if we want to have mutable state, which could be fine, but in this case we'll do a functional approach. So we will disregard the class-based approach and we will consider the other 3. So let's explore some of the ways in which you could model the robot. An option would be to model it as a record. So we could say type robot is curly braces, and then we'd say direction is of type direction, and position is of type position. So this would be a record type, and record types are immutable, and that's one way in which we could solve the exercise. Another would be to have a robot be a tuple. So we could say, hey, this is a tuple of direction and position. And that's also definitely an option. It is one of the benefits of this approach is that you could use built-in functions like FST and SNDs, first and second, to work with the tuple values, and it allows for easy deconstruction, very lightweight, and tuple doesn't have a lot of overhead. Which is fine, but I think the approach that I would prefer us to use is to model it as a discriminated union. So we're going to say type robot is robot of, and then you could do direction and position. It's very similar to a tuple, so you can almost see it like a wrapper of a tuple, but it's now it has a type-safe wrapper around it. So we could have different robots. So even though we don't, this is extensible later on. So if we want to have, I don't know, another a mega robot that has, I don't know, weapons or whatever, or it can move a lot faster. You could have it in a different robot and be extensible, and those other two approaches are less extensible. It still allows for the easy deconstruction that you get with the other types too. So I like this quite a bit. One thing that you can do with discriminated unions is you don't have to specify names for its values, but you can, and I would highly recommend you doing so, because it's basically documentation and it allows for better intelligence, etc. So we're going to go with the discriminated union approach, but the other two approaches would be equally fine. It's mostly a matter of personal preference. Let's start building out some functionality. The first approach that I will be using is a recursive one. A lot of the functionality in this approach will be shared with the other approach, so we'll just do a tiny bit of tweaking at the end, but the first steps are all the same, but keep that in mind. So let's focus on the create function first. We now know its return type, which is robot, and we can return a new robot just by calling its constructor and passing in the direction and the position. And let's run the test, see if we have anything that is passing, and we do have two tests that are passing, which are testing if we create the robot with the right values. So that's all good. What we now want to do is we want to implement the various things that the robot can, the various ways in which it can change. So we have the move left, move right, and advance functions. So let's implement those. Let move left, and it takes a robot, and what it will do is we'll return a new robot. So the discriminated union is immutable, which means that we can't actually change its value. So for something to change, we have to return a new instance. So what we will do is the moving left depends on its current direction. So we're going to say match robot.direction with, and then we'll say north. So if it is north, then we should be looking at west. Okay, but how do we do that? And this doesn't work. What's all this about? So, well, this dot notation is something that you are using if you would model it as a record. But that's not the case with discriminated unions. So with discriminated unions, what we can do is instead we can do the type matching directly within the parameter, or we do it inside the method. So we could say match robot with robot, and then say north, comma, underscore, and then we could do robot west, comma, oh, but we can't use the underscore, so we have to do position here, because we need that for its return value. So this is one option that we could do. And another is that you can actually do this deconstruction as part of the parameter definition. So instead of having the robot thing here, which we don't necessarily need, we can say deconstruct the robot into a direction and a position. And then we can say we're going to pattern match on the direction. So we're going to get rid of all this, and then we can return this. So this is a way in which you can, this shows you how easy it is to work with discriminated unions, and that you can do the deconstruction in the pattern matching immediately in the function parameter itself. So I'm just going to make some copies. So north goes to west, east goes to north, south goes to east, and west goes to south. So I'm going to do a little aligning just to show the regularity of it all. So this is our move left function. And the thing that you have to remember here is we do the deconstructing, so the pattern matching of the robot directly within the parameter. This is still all type safe. If you pass in something else, then a robot, it will fail, compile time. And then we create a new robot with the same position, but with a different direction. So we can apply the same logic to moving right. Well, same logic, almost the same, of course, because we're moving in a different way. So north goes east, east goes south, south goes west, and west goes north. So this is all similar logic, but with different values. So now we can move left and right. Then the next step is to advance. So function is similar in that we have a robot and we have a direction and a position, and we return a new robot. And this time what we're going to do is we're going to again match on the direction. So direction, so we have north. So if the direction is north, if we advance, that means that its y value is increasing, but we're moving up. So this means that the new robot is the same direction, so still north, but the position must be different. So we want to get at its x and y value. So one way in which we could do this is to say we're going to do x and y is position, and we're going to say that the new position is x and y plus 1. Okay, and we can do something analogous for the other cases. So east means x plus 1, same y. South means y minus 1, and west means x minus 1. So I'm going to do a little bit of aligning again, just to show you that the pattern a bit better. So we can see moving north means incrementing the y value, east incrementing x, south decrementing y, and west decrementing x. So we could do this. We could also do the deconstruction directly in the parameter. So this is the same thing, and we now have a way to advance the robot. Then we get to the actual recursive part, which is to apply the instructions repeatedly on the robot. So what we're going to do is we're going to introduce a helper function. We'll call it doMove. And what it will take is it will take the instructions, but not as a string, but as a character list. So that makes pattern matching easier when we do when we implement the function. So we have it as a string here, and we're going to convert it to a character list. Then the second argument is the accumulator value, which is the actual robot. And in the end, what we do is we return a robot. This will be a recursive function, so we're going to add rec here. And then we can do pattern matching. So we're going to say if match instructions with, and then if the first character is an L, and this is the remainder, then we're going to do so what is the next thing that we need to do? So we need to move the robot left, and we need to continue the recursion with the remainder of the instructions. So we're going to call the function itself, and the instructions are now the remainder. So this is the same as the original instruction, but with the first L stripped off. And then we're going to say, was it move left, and then pass in the robot. So the new robot's state that is used in the next iteration of doMove is the one that is the result of applying move left to the robot. So next thing to do is move right. It's very similar. And the final one is advance. And that's advance. Okay. Then there are basically two different things that we also need to consider. One is if it's empty, it's usually the first check. And if it's empty, we just return the robot. And one other case is that we can't do any of these matches, so it's not empty and these letters are not correct. And we'll just throw an error and it's unknown instruction. So this is our recursive implementation. So just to be clear, the instructions are character lists. If we match the empty list, then we're done with all of our instructions. So we just return the robot. If it's a L, we recursively call the function with the remainder of the instructions, but with the robot updated by applying the move left function, move right similar, advance similar. And then in the end, what gets returned is the updated robot. So now the only thing that we need to do is we need to call this function, of course. So we have to convert a string to a character list. Now a string is also a sequence of characters. So we can use sec.toList on the string, and we just pass in the robot. And then we can run our test, and hopefully we should have passing tests. And we have everything passing here. So one thing that we could do is, because this is just there for the benefit of the move function, we could move this here. You could even apply that to the advance and move right, move left, and make that also private. That's one option. We could also say these are private to indicate that they are not to be used outside of this module. I think this is fine. You could theoretically maybe have some use for having the advanced function be called from another function in this module, but it would be much more unreasonable to expect the doMove function to be called, which is why I have this as a nested function and I don't have the others as nested functions. So that's our recursive approach. Then for our other approach, we'll be using a fold. And a fold is a way in which you encode like doing recursion. So a fold is recursing over every element in a sequence or a list. And that's exactly what we need to do. So you can think of sec.fold as having this recursive pattern that we've just implemented built in. So we actually don't need to change much. Just a couple of things. So we're gonna get rid of this and we're gonna say sec.fold and see what we need to pass into. So there are 3 different parameters. So the first is the function that takes the state, it takes the value of the sequence, and it returns a new state. So the state will always be the robot, the value in the sequence will be the character, and then the other parameters are the initial state and the initial sequence to operate on. So we'll skip the folder for now. The initial state is our robot, and the initial source is the instructions. And once again, we convert that to a list. Or do we? Well, that's the thing. This time we use sec.fold. So as we are not doing the recursion ourselves, it's fine to use a sequence. So we don't actually need to convert the string to a character list, but we can just keep it as it is. The only thing that really changes is we can't just plug in doMove here because it has the wrong type signature. So if you remember, the fold takes a state, then the element, and returns a state. So we have to do a little bit of reordering. The state is the robot and the element is actually the character, so not the character list. And then we can match the instruction with a character. So we get rid of all that remainder and recursive stuff. Speaking of which, I can remove the recursive modifier and just do this. So I'll leave this for now. So you can see that previously we had to recursively call something and we have to take care of the remainder, but we don't need to do that right now. That's all built into sec.fold. So I'm just gonna do this. And this is doing the exact same thing. And just to verify, let's run the tests. And we still have passing tests. So in general, doing manual recursion is often not needed because there are so many built-in functions that do that for you. And sec.fold is a perfect example of that. We have less code to maintain. There are compiler optimizations that can be applied to sec.fold that it might be harder for you to do. So in general, I would recommend you not writing manual recursion if there is a corresponding higher order function that you can use. And with sec.fold, you can. Our third way in which we could model the robot is via a record. So let's try and see how that changes things. So we're going to model the robot as using this syntax, direction, and then position, colon, and then closing it with curly braces. Then we need to change the create call because records are created in curly braces. We need to assign the individual and we need to convert this to a comma. One thing that we could do is the compiler will now infer its type based on the names and the types. That could theoretically be a different record with the same types. So you could say robot.direction, but I think it's fine for us for now to leave it like this. Then what we're going to do is, in this case, we're going to try something differently. So this is no longer valid. So we could do just have this be robot, and then we'll make that of type robot, and then we'll do robot.direction. So then we say, hey, this all works fine. Oh, sorry, forgot the colon here. But if we want to return a new robot, we want to create a modified instance, so a new instance of the record. And that you can do with robot with, well, several ways in which we can do it. We could do the explicit way, robot is west and position is position, robot.position, which would be fine. But this pattern of having a record and then modifying just one of its values, or maybe a couple, without modifying them all, there's also a different way in which you can do that, and that's more idiomatic. So you're saying, do the curly braces and then start out with the thing that you want to modify, and you're saying with. And this, you can think of this with as everything that comes after is the things that are changed. So you're basically saying here, return the robot, but with its direction set to west. So let's do that for north, east, and south. So do something similar here. It's east, and we of course we have to say that now we have a robot parameter, and we're using the dots. So you could say that the dots, being able to dot into the type is a benefit of the records. I would be totally fine with you saying that. So north, okay. Then this becomes slightly more of a chore. So we're going to say robot is robot, match on robot.direction, and we're going to say robot with direction, position is okay. And then what we do, we say robot.position.x. No, that's not valid, because the position is not a record type, because position is a tuple. So what we can do is we can do a couple of things, but the most simple one is just do x.y be equal to robot.position, and then we can reuse what we have. So we're going to apply this to the other cases too. Do this here, do this here. And then we add the, sorry, I should have probably copied that like this. And then we have everything being in a valid state. So let's run this. And still everything passes. So you can see with a record type, there might be need for more annotations. Not always the case. It depends on whether or not you have conflicts. And changing things has a different syntax, but you are able to dot into things, and that is quite an advantage, I think. And then finally, I do want to show you that you can do deconstruction of records too in the parameters. So let's change robot to be direction is direction. Oh, whoops. And position is x, y. And we can get rid of the parentheses. So we now have, we don't need this, but well, we are not really interested in direction. So we could do direction is direction, comma, but we could even do something differently. So as we're not really that interested in the direction here, we could remove it here and just say robot directly after the pattern. And oh, we do need direction because we have it here. So you can say robot, and that will be the thing that is matched before it. So that is the entirety. And we still can match the individual record things. So, but for here, for the move right, we can change it to be direction is direction, and then robot. And then we can move the direction out of it. I'm not sure this gives us much. I've seen people do this, but I'm not a huge fan. I think for when you work with records, it makes less sense than when you work with tuples or discriminated unions, and that's also one of the reasons why I chose to model it as a discriminated union. But feel free, if you like this, to do it this way. It's very flexible, and you can, but you get these big parameter definitions that you may want to look at if they're still readable. As an addendum, I thought it might be nice to check how things would look like if we would have modeled the robot differently. So I mentioned 2 other idiomatic options. So let's see how things change if we use those. So instead of modeling the robot as a discriminated union, let's just model it as a tuple. So we remove the names, and we now have the robot just be an alias for a tuple, just like position is. And then what changes is we get rid of the robot types references. So we no longer have a constructor call. And then we can get rid of robot. I forgot to do that here. Do it here too. So here and here and here and here and here. And that should be it. And let's run it. You could even, if you'd like to, omit the closing and closing parentheses. So we could say it's like this, and then do the same thing here. We do need them with the tuples on the right. Run it again. And we now have a tuple-based approach.